Today, let us learn Lindemann's mechanism. According to collision theory, for a chemical reaction to occur, the molecules with energy equal to or greater than the activation energy must come in contact uh, in a proper manner. And so when this collision is happening, all gaseous reaction must be bimolecular or second order. But this is contradictory to the fact that because it is found that the gaseous decomposition reactions, many of the decomposition reactions like decomposition of nitrogen pentoxide and all, it follows first order kinetics. Lindemann actually explained how a bimolecular collision can give rise to the first order kinetics. According to Lindemann's theory, the energy that is required for breaking of the bonds of a gaseous molecule is very high. Okay, and this energy is acquired by a gas molecule A. So let us consider a gas molecule A, and this energy is acquired as a result of collisions with its neighboring molecule. So at another neighboring molecules, let us consider another A. So now a gaseous molecule A is colliding with another gaseous molecule A, and the energy that is gained by a molecule will be, or is it thus at the cost of the energy of its neighbor. Okay, and as such, this event must be included as one of the steps of reaction mechanism. So this must be included as the reaction. So let us see. So when A is colliding with another molecule of A, it results in the formation of an activated gaseous molecule and the other molecule. Okay, so let the rate constant for this reaction be K1. Okay, and secondly, and the activated molecule. So activated molecules, this do not decompose immediately. Okay, so the decomposition of activated molecules will not take place immediately. This will remain in the activated form for a finite period of time. Okay, that means there is a time lag. And during which it may get deactivated by the colliding with a normal molecule. So again, either it can get deactivated. So let this backward reaction be having a reaction rate constant K2. Okay, so here we have A colliding with A to give an activated molecule, which is A star. Okay, and so this has possessed sufficient energy that will can undergo decomposition. Okay, and sometimes this A star, that is A star, can decompose to give products. So let this reaction constant be K3, and this can give you products. Okay, so these are the considerations, or these are the concept that was explained by Lindemann in order to explain the kinetics of unimolecular reaction. So now we have K1, K2 and K3. So here A is the reactant. Here it is forming the product. So A is converting into product. In between we are getting the activated reactant molecule. Okay, so this is the activated reactant molecule. Okay. And we know that according to steady state approximation, so if you take according to steady state approximation, rate of formation of this intermediate, rate of formation of intermediate. So let us consider here, which is the intermediate? Intermediate is A star. So rate of formation of A star is equal to rate of decomposition of A star. Rate of formation is equal to rate of decomposition of A star. Now what is rate of formation here? What is rate of formation? So here we can write the rate of formation of A star is equal to, so here in the first step it is forming, so we can write the rate equation as K1 into concentration of A into concentration of A. And the rate of decomposition, in no other steps A star is forming. So here A star is decomposing back to the gaseous molecule. Here A star is decomposing into the product. So the rate of decomposition. So we can write the rate of decomposition of A star is equal to, so here we can write as a sum of the two steps. So rate equation, we should involve the two steps. So the first step we will take the decomposition of A star to back to the gaseous molecule. So here K2 A star K2 A, which is the next step. Here this is the next step in which A star is decomposing, that is decomposing into products. So K3 A star. Now we know that as per steady state approximation, rate of formation of A star is equal to rate of decomposition of A star. Therefore we can write K1 A square is equal to K2 concentration of A star into concentration of A plus K3 A star. Okay, and we can modify this, or this implies K1 A square is equal to, the common factor I will take it out, this is A star, concentration of A star, we can move it out, then we can write K2 A plus K3. Therefore concentration of A star, so I got now the concentration of the activated gaseous molecule. Concentration of A star, I can write it as K1 A square divided by K2 A plus K3. Okay, but we know that rate of this reaction, so as according to this particular step, rate is that is the product formation. So if you consider the product formation step, we can write that the rate of a reaction is equal to dP by dt is equal to, now rate of a reaction can be written as, so we know that rate of this particular reaction we can write it as, so if you consider P as the product concentration, so it is dP by dt. This is equal to K3 into concentration of A star. So the rate of this reaction we can express by substituting the value of A star. So therefore rate of this reaction, so we can write rate is equal to, so here K3 is there, K3, then we have to substitute for A star, concentration of A star. So it is K3 K1 A square divided by K2 A plus K3. So this is the equation for, this is the rate equation we can calculate using the steady state approximation and the Lindemann concept. Okay, so now let us consider two different cases. Okay, so the case 1, so let us consider two different cases of this. So let us consider case 1. Case 1 is the reactant concentration is high. So the reactant concentration is high means K2A. K2A is very much greater than K3. So our reactant concentration is very high. So that means K2A is very much greater than K3. So our rate equation is K3 K1 A square divided by K2A plus K3. So here the concentration K2A, this term is very much greater than K3. Okay, so we can write the equation. So when this is, we can K3 can be eliminated. So when K2A is very much greater than K3, so we can eliminate K3. Therefore, rate can be written as, rate is equal to K3 K1 A square divided by K2A. Now we know that A and A can be cancelled. Therefore, rate is equal to K dash A. So what it represents? When the reactant concentration is high, the reaction is of first order. So this is only depending on the directly proportional to the reactant concentration. That means this follows first order kinetics. Okay, now let us consider case 2. So case 2, what can be case 2? We are considering K3 is very much greater than K2A. That is, reactant concentration is lower. So the product formation is high. Okay, so we are considering the product formation is high than the concentration of the reactant. So in such case, K3 is very much greater than K2A. So from the denominator, we can eliminate K2A. So if you eliminate K2A, rate we can write as K3 K1 A square divided by K3. Okay, K3 K1 A square divided by K3. We have eliminated K2A term. Okay, we have eliminated the K2A term. So rate can be written as K3 K1 A square divided by K3. Here in this case, product formation is high. That is, the conversion of the activated molecule into the product is high. So in such case, we can write this rate. So again, all these K3 K1 K3. From here we can reduce K3. So I can write it as K1 into A square. Now this is the rate equation for a second order reaction. So here it is second order kinetics. Here it is second order kinetics. Okay, so this is how we can explain the unimolecular reactions undergoing second or following second order kinetics or first order kinetics.